Fine. So welcome to a new lecture of the data management and visualization course. I'm just kicking off this. Okay. So if you are in the Zoom meeting, could you please confirm that you can hear my voice and see the screen share with DFM hierarchy? Please drop me a line in the chat. Thank you. Thank you. Francesco Samed, great. Okay, fine. So where are we? We are studying data warehousing. We have learned how to create the conceptual design of a data warehouse. This is the schema which will drive us through the data warehouse design and specifically the conceptual design. Okay, so here we fill in the concepts. Okay, it's not the tables yet. Later we will do the logical design, which consists of creating the tables. But before that, we create the conceptual model. Okay, in the conceptual model, we put what? First, the fact table. The fact table is the core of the data warehouse, which describes the events of interest. Okay, the sale, if you're analyzing sales, the temperature sensor, the grades of students, okay, the things you're interested into analyzing. Okay, these things, these events, temperature, grades, exams, sales, and so on, are described by quantity measures. Okay, so inside the fact table here, so the name of this fact table is sale. Okay, and then we have four measures in this case. Okay, which describe the event of interest, the sale. Okay. Then we have the dimensions. Okay, when we want to analyze the sales in this case, the sales are events which happens in a specific shop for a specific product and for in a specific time instant. Okay. Here we report in the dimensions the level of interest we want to analyze. So in the original database, not the data warehouse, the original sale database, we have the time with the minutes, the hours, the seconds of the sale. Okay. Here we have only date. So this means that all the sales happening in the same date and having also the other features the same, so the same product, the same shop, will be compacted into a single row of our data warehouse. And that is the difference between the original database and our data warehouse. Okay, so the data warehouse typically aggregates the original data. Okay, one row of the data warehouse generally describe homogeneous events of interest. Okay, so in this case, we have date, we have product, we have shop. Okay, so when we have multiple sales, so multiple times that customers go into the same shop for buying the same product in the same day, so in the morning, the afternoon, and so on, all those sales are different rows in the original database. Okay, but the same row in our data warehouse. Okay, and when we compact the input data, so the data coming from the original database into our data warehouse, we write the sold quantity being the total of the sold quantity, because that sold quantity means how much items did you sell for that product in that shop on that day? 100 items. Okay, the sold amount, the sale amount. How much did you? How much money did you get from selling that product in that shop in that date? Okay, and so on. Okay, which was the unit price of the product? How many different customers? So many probably purchases tickets you have, or if you have a loyalty card, then you can actually count the specific different customers. So the same customer coming more than once at the same day for the same product for the same shop, you can count it only once because you have a loyalty card, okay, for instance. So that's the idea. So these are the basics, okay? If you're all aligned in these, we can go on and see the rest. We actually went on last lecture. We have seen the comparison with the entity relationship. We have seen some advanced structures. I recall you, we use the convergence, and basically we don't use much of the others. I explained you why, because they are kind of optional, or you can easily work around those advanced constructs, okay? We'll see others later. Then we discussed about the aggregation of the measures, okay? So choosing the right measure is important. And specifically, we have seen stream, level, and unit measures, okay? That was the towards the end of the last lecture. Actually, we finished a little further. We arrived with operators. Yeah, we've seen these examples of the aggregates. And we arrived at slide 27, I guess, which is, I wrote it here. Yeah, the shared hierarchy that explained that. Yeah, we have seen these, the multiple arc, the multiple edge solution, okay? And the last example was in the configuration attribute, okay? So these are all patterns that we will apply, okay? So these patterns of the average, so here the point is the average is a problem, okay? Why the average is a problem? Let's recap that because this is important. If you have in your data warehouse a measure which is, for instance, average grade of the students, okay? So here I build a data warehouse like this with some dimensions, okay, as you wish. Here you have exams, and then I write average grade, okay? Copy these with an exclamation mark because this drives you to fail this exam, okay? So this is not to be done. This is a wrong pattern I discussed, okay? Why it is a wrong pattern? So I'm interested into you understanding why, okay? Not just learning by heart. The average grade is something that is difficult to manage because if I have many averages across exams, across academic years, across different dimensions, I cannot just do the average across an academic year and then do the average across different academic years, okay? Imagine that you passed 10 exams last academic year, okay? And you passed only once this academic year, okay? If I do the average separated by academic year, which might happen because in the data warehouse, you have different dimensions, okay? So you group by academic year. You do the average. You have the average of the past year out of 10 exams, okay? You have the average of this year out of 1 exam, okay? Then you want to compute the final average, okay? And you do the average of the averages. So the average of last year and the average of this year. That's wrong. That's not your average grade, of course, okay? So that's a mathematical problem. It's not a data warehousing problem. The problem is that warehousing is relying on mathematics to do the statistics and averages, and then it brings back all the consequences, okay? So knowing that in data warehousing, we are continuously working, and you will see that during the extended SQL and the queries we will do in a few slides, in a few lectures, okay? We are continuously querying the data warehouse for statistics, for analysis, for averages, for maximum, minimum, sum, count, all these aggregate measures to take decisions. Okay, so what's the average grade of the students? Is it decreasing? So is it the teacher getting more strict? Is it the teaching degrading the teaching capacity? Okay, why is the average grade decreasing? Okay, so you need to understand the trends, the overall trends, okay, to take decisions and see, do we need another teacher? Do we need to change the course? Do we need to do something? Okay. Then, if you have the average as a measure, you are kicking your ass, okay? Because, and that's the problem. You're just doing a wrong choice. Okay? You're making things worse for your life. You need to query this. Okay. Instead, since the average is simply the sum divided by the count, okay, and the sum is aggregative across any dimension typically, okay, so the sum of your grades, you can sum the grades of any academic year, of any exam, of different dimensions. The sales, the sum of the sales, so the income, the number of items, you can absolutely sum them as along any dimension. We have seen these into this, okay, this slide, okay. So the sum is a measure that you can easily aggregate across many dimensions. The count, the same. Okay, so if you take as an example the sales case, we have, or is it the, well, we don't have it there. We have the example with the sold quantity, so that's the number of items, and the sale amount, that's the amount in euros. Okay, if you take the two, you can easily compute the average income per item. Okay, so instead of writing average income per item here, I write total number of sold items, total number of items sold, total sale amount. Okay, I work with those two measures along any dimension. I group them by shop, by date, by product, by diet, by anything. Okay, at the end, when I have the totals of the amount in sales and the amount in items, I do the ratio of the two and I get the average amount I get per item sold. Okay, and that's correct because I'm summing 1,000 items. I get the income for those 1,000 items. It works by definition. Okay. Instead, if you had written there average income per item, that wouldn't work. Okay, it might work in some cases, but generally that doesn't work across all dimensions. Okay, you end up having the same as the example I gave you. So the average grade for one academic year, the average grade for the other academic year, but they don't match. You cannot do the average of the averages. Okay, so that's the problem. So in general, no average. Okay, no average. That's definitely a bad idea to have an average measure there. Okay, so this is wrong. Okay, no average grade, no average something in the fact table as a measure. Okay, instead introduce the sum and the count. So if you have a customer or your boss or the teacher at the exam asks you to track the average income per unit of items sold, okay, this means that you have to insert the total amount of the sales and the total amount of items. Okay, so that specification, please keep track of the average amount per item sold or the average grade of a student, is translates into two different measures to be inserted into a fact table. Okay, we'll do these many times during the exercises as well, but let's focus things now. Okay, then the last was the configuration attribute. So that was the average. That was, yeah, the share hierarchy. So if you have two hierarchies which has the same domain, which means they contain the same data basically, even if with different meanings. So I'm calling from a number to another number. Okay, but the numbers which can be receiving the call or sending the call are the same domain. Okay, you use a shared hierarchy. Okay, this has many advantages because if you fix one of them, you fix them all. They cannot diverge. Okay, you cannot have two different sets of numbers. When you update the table containing all the numbers, you update them for both dimensions, both the sender of the phone call and the receiver of the phone call. And you have only one copy of the data. Okay, so also as a storage space, it's better. Okay, how this will translate into a real implementation, we'll see it later. But simply you have two foreign keys. Okay, you might get this hint or not, but we will see that later. Okay, and then yeah, we had also the multiple edge. Okay, so let me spend a few minutes on the comparison of these two options. Okay, so you have the multiple edges. So let's do it here. So you have the reference. That's the book and the author. Okay. Yeah, I'm not good at drawing, but that is, okay? Why the book is missing? Book. Okay, it doesn't work. But anyway, that's simply a copy of this book author relationship, just to have a comparison, okay? So in both cases, you are associating, in one case, the book, in other case, the store, okay, to something which has a multiple possibility of being evaluated. Okay, so the store can be selling toys and mangas and accessories, or toys and mangas, or toys and accessories, or collectible, and so on. So you can have any combination of these four items. So it's a kind of a multiple relationship. The book can have many authors. Okay, so in some sense, if you draw something like this, with the book here, okay, and here you have the authors, okay, so here you have author 1, author 2, author 3, author 4, author 5, okay. It's similar. In concept, it's similar because I take a book, like if it were a store, and I say, is this book written by author 1? Yes or no? Is this book written by author 2? Yes or no? And so on. Okay. So in concept, they're very similar patterns. Besides the drawing with double edge or whatever, they're very similar. Okay. And indeed they are. What's the difference? The difference is in terms of efficiency. So if you have a small set of features, like it is for the store, I have 4 features for the store. So the combinations are 2 to the power of 4, 16 combinations, okay, of these yes, no collectible. In case you have, no, 3 state, like yes, no, I don't know, or yes, maybe, no, okay, can be 3 to the power of 4. But anyway, it's a very low cardinality, okay, it's less than 1,000, let's say, overall. Then this option is better, okay, because it's easier to be managed. We will see later during the logical design that the solution with the store option, that the configuration attribute, doesn't require a join operation. Okay, the join operation, for those of you who haven't done SQL, but you should have reviewed something, is to match 2 different tables, okay, so that a kind of attribute matches, okay, indeed. The join operation is among the most computationally expensive operations for a data warehouse and even for a database, okay? And for this reason, it has tens of years of optimizations. Okay? It's a core part of databases, relational databases. Yet it is expensive. So if you can avoid the join, it's better. And if avoiding the join does not introduce any additional cost, even better. It's more efficient. So when the number of options here, so imagine these are yes, no, or a 3 state, yes, no, I don't know. But anyway, a very low number of options can be something like no, low, medium, high. Okay. So you multiply all the possible options, okay, and you obtain a number which is small. The problem of being small is that we need to decide a reference to be used in our agreement of the course to verify the exams and also in real life. Okay? In general, we always consider 1,000 as the limit. Okay, so 10 to the power of 3 is the boundary. If you're higher, you go towards another solution. In real life, if you have a very powerful server, you can also arrive to 10 to the power of 4 as cardinality. And this configuration attribute is still convenient, okay? But for our course, because we need to have I would say, a boundary to say this is wrong, this is correct, and evaluate yourself, we choose 10 to the power of 3, okay? Up to 10 to the power of 3, sorry, that's very badly drawn. It is acceptable or better, it is convenient, and so you must choose the configuration attribute. Okay, 10 to the power of 3 is the number of possible combinations of all the values here. So collectible is yes, no. Toys is yes, no. Mangas is yes, no. Accessories can have, I know, 5 values. So 2 multiplied by 2 multiplied by 2 multiplied by 5, that's what I mean. Okay, the possible combinations. What about the book and the authors? How many combinations do we have? I would say virtually infinite. Okay, so there are millions, billions. Okay, because for each author you can have yes, no, but authors are, you name it. Okay, either it is just the books at my house, but even in this case, it's very high value. Okay, for any kind of data warehouse storing books, it's unfeasible to have the configuration attribute to link the books and authors. Okay, because that will create a table where each author becomes a column of the table. And you cannot have a table with millions of columns. Okay, that's let's say common knowledge for database guys of you who already studied databases. But I will tell you, if you haven't yet, that's impossible. Okay, so when the cardinality of the possible combinations is very high, then you use the multiple arc, okay, multiple edge solution, okay, at the expense of an additional join. Okay, we'll see that during the logical design phase, okay, but I anticipate because that's the reason why we study both patterns, okay. Typically at the exam, I always ask either one or the other or both, but I tend to evaluate you on these choices because these are kind of let's say among the typical choices you need to face during real life exercises. Okay, whether choosing the fact table or the measures, I mean, it's not so difficult in general. Okay, I still find some students, probably they didn't attend the lecture, I don't know, who put the average, but generally 95%, 98%, they will not put the average, and it's not so difficult. You tend to sometimes have problems in the hierarchy. If I don't give you standard hierarchies, which you just copy or by heart, someone gets strict on the hierarchy. But otherwise, the typical difficulties are in these patterns, the configuration attribute and the double edge pattern. Okay, so you can focus also on the key points of data warehouse design. Okay. Fine, so that's all, most of the advanced structures in data warehousing. Now let's check another case, which is borderline, I would say. Sometimes you have fact tables without measures. Okay, why? Because the only thing that you have a row describing the combination of student, course, and semester means that the student, I don't know, has attended the course in this case. And you see, it's called attendance, or has passed the exam, or has done something, has delivered the homework, okay, has done something of interest. Okay, so if you only need to check the presence, the event is a kind of yes or no. There is the event or there is no event. Okay, I participated in a event, in a party, in a course or not. You might have this situation. Okay, so apparently there are no measures. Actually, there is an implicit measure, which is the existence of the row in the data warehouse. So you can actually count how many students attended the course in that semester. I can answer that question because I counted the number of rows in the data warehouse. And that gives me the number of students in that semester in that course. Yeah. Okay. So that's a very extreme case. Typically, we tend to enrich, okay, the fact table with additional measures, but it's not compulsory. It depends on your requirements. Okay, so that is the case. In this case, the presence of the row means I attended. If I didn't attend, my row, so the row with my student ID for that course, for that semester, is absent. Okay, another option would be to have a measure 0, 1 and have all the combinations. And so the presence of 0 or 1 tells me if there is the presence or not. What's a drawback of this second option? The size in storage. Okay, so if at Polytechnic we have, I don't know, 30,000 students, okay? We have, I don't know, 1,000 courses, okay? Well, we have 2 semesters per year, so we can have different semesters, a few semesters of the last years. If I write only the presence with a row, I'm writing only the combinations that actually exist. If I fill in the data warehouse with zeros and ones, okay, so the measure here is not an implicit count, is actually present 0, present 1, with 1 being it is present and 0 being it is absent. I potentially store all the possible 30K students for all the possible 1,000 courses with a lot of zeros, which is useless because also storing 0 occupies disk space, totally useless. Okay, so that is the wrong design one might think of, and I don't like you to propose, okay? Because that would be a total waste of space, okay? If you have sparse data, you tend to materialize, to store only the sparsity, so only the combinations that exist, okay? Instead, if you have a dense data set, of course, you can store 0, 1 because the ones are the most. And so you can also add some zeros, but that's not changing your overall requirements in terms of data space, disk space. Okay. So that is the case for the factless schema. Now, one important stuff we need to address in data warehousing is the following. At the moment, we are saying the following. We are saying that we are tracking sales or temperature or grades of something. So the change, the things that changes is the measure. The sales are changing, the temperature is changing, your exams are changing because you take new courses, you pass new exams. However, also things in the dimensions might change. So if I move this sensor, or if I close a shop, open a new one, or if a student changes CD, okay, then something in the dimension might change, okay? And this is called, as a problem, the slowly changing dimensions. Why slowly changing dimension? Because this, of course, might happen, okay? So imagine that I want to analyze the average grade of the students depending on the country they come from, okay? And as a country they come from, I take the country of the, the official address, not where they were born, but the official address. So if you come from abroad and your official address is still abroad, I count you as an abroad student. If you move and you set your address in Italy, then you become a student with an address in Italy, okay? That's an example. Other examples include people and in sales, customers in sales. I take a customer and I group the average amount of money spent by people who is married or not married, okay? One can get married. And so the same customer becomes married while I'm tracking the performance of the customer. And so the problem is, if the change is in the measure, no problem, because the measure, like temperature, the sales, the grades, are meant to track something with changes. But if I change, I don't know, the name of this room, the position of the sensor, or the status of the customer over time, the change happens in the dimension. Whose purpose, if you look at dimensions like this is meant to be stable over time. Okay, if I change dimension, I'm kind of breaking the data house. So I've done an effort to design this, and then this over time shifts, drifts, changes away. Okay, that's the reason for the slowly changing dimension problem. Okay, slowly changing dimension is the name of the problem we are addressing now. It's slowly changing because if these values, okay, let's take an absurd, okay, I have a customer who one day is married, the other day is not married, then again it's married, then not married, or a student who every day changes the place of its address, okay, in different cities, okay, that doesn't make sense. Okay, it's an exception, it's something which doesn't work in reality, okay, because otherwise my problem would be not tracking the sales or the exams, but tracking the chasing the student who is going away, okay, around the cities, okay. So the idea is I design my data warehouse like this with dimensions, students, semesters, courses, and so on. Some of them might change over time due to these examples. Okay, then any use case has its own examples. Okay, how do I address that? Okay, because if I change something in the dimensions, this breaks my data warehouse. Okay, why? Well, simply because if we take an example with an Excel sheet, I'll show you what happens. So we have also the example for describe the next slide. Let's move it here. Okay. No, sorry, it's there. Okay. Let's imagine that we have, okay, we have the customer ID, the status, married. Okay, let's take this as an example. Then we have, well, the shop, the date, and the sale amount. Okay, so a given customer in a given date, in a given shop, has spent a given amount. That's our data warehouse. Okay, I'm adding the married status to determine, okay, the change, to explain the change. So I have customer C1 in shop S1 yesterday, okay, spent 100 euros. Okay, now, and also some customer C1 in shop S2 yesterday and spend 200 euros. Okay, now if I look only at this table, I can say this is married, no, then it gets married, I have a yes here. Okay, this seems to be easy. This is wrong. Why? Because in our design, okay, so I'm sorry, I get back to the slides for a second to show you what's the problem. Where is my slide deck? Here, okay. What's the problem here? It's the following. I have a customer here. Then I have the shop. Okay. Then I have, what was there, the product? I don't remember. Was the, no, shop date. Okay, the date. The shop, that is the date. Okay. Then the customer can be grouped as married or not married. Okay. To have an attribute, to analyze my data according to that attribute, the attribute must be in one of my dimensions. Okay. And married, I can group all the customers being married at a given point in time or not. Okay. So married is in the hierarchy is higher than customer, as it is the city. Okay. I can group all the customers living in Turin, all the customers living in Milan, and so on. Okay. Given a customer, he or she lives only in one city. I take the principal address. Okay. Given a customer at a given time, it is either married or not married. That's it. So I can group them all. That's a functional dependency. Okay. But if I introduce this case here, there is no functional dependencies between customer and married. But the same with city. So if I replace this with city, Okay, so another example can be city. Okay, here. Let's say this is, well, yesterday it's a little difficult because in the same day cannot be both states. Okay, so let's do it a more credible, solution, which might be like today. Okay, then introduce a new blank line here. Okay, and so here it will be probably Turin as well. And then we have another one, which is instead Milan today. Okay, that's the case. Okay, in both cases, being in married or not, or a city, this person got married and moved to Milan. Okay, yesterday wasn't in Milan, wasn't married, then got married and moved to Milan today. Okay, so it changed the behavior. Okay? So I cannot implement this in data warehousing because I break the functional dependency between the customer and the city and the customer and the married status. Okay, so how can I solve this problem? Okay, and there are basically, let's say, 2 solutions and a half. Officially, there are 3 solutions. Okay, so the first solution is since every no, this is no, sorry, no, yes, yeah, okay, that is the right one. Okay, I'm sorry about it. Okay, no, and yes. Okay, so this is the change. Let's highlight this with so you know this what's wrong here. Okay, not wrong actually. What's happening? Okay, so first let's fix simply the functional dependency. Okay, to fix the functional dependency, I can say that this customer is another one. Okay, so this was the famous Mario Rossi, which is a very famous name in Italy. Okay, it's like John in any other country. Okay, Mario. Okay, okay, so it's always the same. He is exactly the same person. However, to keep the data warehouse working, and it requires the functional dependency, I decide that when the Mario Rossi gets married or changes city or breaks any other rule of my hierarchy, okay, I give it to him a new ID. It's like if it were a new customer. Okay, that's the easiest solution. Okay, it has some drawbacks. If I ask my data warehouse, how much money did I get from Mario Rossi? You don't know because I wrote Mario Rossi here for your reference. Otherwise, you can understand my screenshot when you take the picture. But actually, C1 and C2 are simply 2 different IDs. So well, I can count for C1, I can count for C2, I can count for C3, which is Mario Verdi, but they are totally different. There is no link between them. Okay, they're absolutely, totally different information. Okay. Another option is I don't want to lose the history, all the information I got from Mario Rossi in the past. I want to force the fact that Mario Rossi is still the same because that is important to my business. Okay. Then, just a second, I get to you. Then here, when Mario Rossi gets married, I change Mario Rossi as being married since it's his birth. Okay, so that's solution 1. Let's copy this. That's solution 1. Okay, then we have solution 2, which is this one. I do like this and like this. Okay, so what happens is that Mario Rossi in this modeling, sorry, C1, okay, he has always lived in Milan. He has always been married, which is his current condition. propagated into the past. And this is easy thanks to the way in which data warehousing stores the logical tables, which we'll see in a few slides. Okay, so solution one, I break with the history, with the past. When you change your hierarchy relationships, you are a new record, a new item, a new customer, a new shop, a new anything. Okay. The second option is you apply the current condition in the past. So I want to analyze the amount of sales to people in Turin. Mario Rossi will not count as people in Turin because now he is living in Milan. And even if he bought items and goods in Turin in the past, and so the previous sales were done in Turin, due to my choice, I count his sales happen in Turin as if they were happening, in the past, they had happened in the past in Milan. Okay? That's the second option. Okay, there is a third option. Do you have a question? Pardon?
I mean, we can add its non-value. It doesn't have any, it hasn't changed. And if it changed, we can replace the usual with the last ID.
Yeah, kind of. So his proposal is to link the two customers. So I think you're referring to this one because this is the case with two customers. And actually, you are kind of anticipating the third option. Okay, so all the possible solutions resort to three options. The two options I've shown you, so create a new customer, that one, or keep the current condition even in the past, second option, please. Sorry, because I was pointing to her. Okay, but didn't get any of them because I was thinking about yes, thank you. That's I didn't. Yes, you're right. I thought I did it. Sorry about it. Yeah. Yeah, because because it goes one more. Yeah, you're right. Sorry. Because I did it again and it didn't work. Yeah, thank you. That's the case. Let's put it like this. Absolutely. You can take the picture now. Thank you. Yeah, that's correct. Thank you. I meant to do that with the drag and drop of Excel, but actually it counts one more when you have ending your string with a number. So that's I didn't get it. Okay. Yeah. So these are the two options, basic options, please. The question is, how can I call these solutions despite all the drawbacks? So the point is, they actually doesn't work. Okay, so they are not solutions. Okay, no, they're actually solutions. First, because data warehousing is a discipline which doesn't come from theory. Okay, so data warehousing is not born thanks to mathematics having big theories or in computer science students having big theories. Okay, data warehousing, if you look if you read the Kimball book, was born from best practices in the companies. Okay, so it comes from real life examples. So it was born dirty, I would say. Yeah. So at the beginning, they used simply databases. Then they understood databases was not enough. You see the entity relationship schema. And so they developed new stuff and was kind of a response to real life requirements. Then we formalized that. And so now we have a kind of a theory or formalism, and we're tens of years away, okay, from that time. But the reason why these are acceptable solutions is that because for the companies, that was enough. So I take this example to give you an idea. Here, if you want to analyze the difference between the average income between people in Turin and people in Milan, you don't care about Mario Rossi. That works. So the drawback, you don't care. If you want to analyze the case of difference in average income between married and non-married people to do promotions or things like this, that works. You don't care about Mario Rossi being the same. Okay. So when I highlighted the drawbacks, of course, I focused on when they are not working. But as most solutions, okay, imagine, electric cars, computers, everything has drawbacks. Okay. I think there is nothing with no drawbacks. Okay. So in the end, if you focus on even the iPhone, the mobile, everything you analyze has some limitations in some sense. So if you focus on that use case where you want to do that specific thing and that doesn't work, Oh. Okay, so your point, I'm repeating your observation. That's interesting. Thank you. We have no way out. So you would like to find a solution which works for without drawbacks in some sense. Yeah. So the point is, today I might be satisfied with having the comparison between married, non-married, or Milan and Turin people. But in the future, I would like to analyze the historical sales of each customer, and they want Mario Rossi to be joined. I have a good news for you. There is a kind of solution here. There is a third type of solution. Just to give you the idea, we have seen this slide, and type 1, type 2, and now we have type 3. Okay. In type 3, we use this solution here, and we do something similar to what he suggested. We link C1 and C2. And we say C1 is valid until a given point in time. C2 is the same customer starting from a given point in time onwards. So for the married, yeah, you can go yes, no, yes, no, yes, no. But for the cities, you can have Turin, then Milan, then Rome, then Turin again. So the idea of the general pattern, which is the most complex, so the drawback is present anyway, because you can manage that. So potentially in the future, when you discover that you need this kind of analysis, you can do that analysis. But meanwhile, you paid the effort, the size, the complexity to maintain something you didn't use. That's inefficient anyway. Okay. So that is the solution. So here we would link C1 and C2 in a separate table. Okay, you have a supporting table which says C1 and C2 are the same, the validity of C1 and up until, and C2 starting from, and then might be also up to until. Okay, so I just tell you this kind of solution is outside of the scope of the exam. Okay, will not ask you to manage the type 3 management of data. Okay, and in general, even in real life examples, this is only used by very big companies which want to do anything and have efforts to pay for people managing the complexity. But generally, type 1 or type 2 satisfy most of the cases. Then it depends only on your setting. If you're doing advertising for customers, you don't care about a specific customer changing the class. Okay, when you have millions of customers, you're generally focused on trends. And when you analyze data on separate semesters or quarters or years, the small change over that period is irrelevant. Okay, so that's the point. Okay, please.
Being married or not, the core thing, what we're measuring, then he is going to definitely a new customer, because I don't see how it's a
okay. Okay, thank you for the question. The question is, I don't see the drawback of this solution here, because if being married or not, or living in Turin or Milan is a founding characteristics, so a very specific feature of how I cluster my customers, then if you change your features, you become a new customer. Okay. The point is, that's interesting as a view, that's correct. However, if you want to analyze what's the average income I get from a customer, it's also called customer value, average customer value, customer lifetime value in marketing and business. Okay, so which means when you need to acquire a new customer, okay, you pay something, marketing, cost of acquisition, Google advertising, Facebook advertising, everything. Okay, it costs, I don't know, 100 euros to get a new customer. Okay, then you want to know, but when I get a new customer, on average, how much money I earn from that customer. Okay, if I'm selling, I don't know, insurances for the cars, for instance, the average insurance for a car is hundreds of euros. So with one sale, I cover the cost of acquiring the customer. So I can even spend more in acquiring customers. Okay, if I don't know, I'm selling small goods, coffee, okay, in a bar, in a cafeteria, in a small food shop, the customer buys, I don't know, 5 euros or 10 euros of stuff. So if I spend 100 euros for getting the customer, and then I get only 5 or 10 euros once or twice or 3 times, that doesn't work. Okay, so that's to introduce the point. I don't want to analyze the customer lifetime value, which is whose estimation is basically the amount of money I get from the customer over a lifetime, which means over a year, for instance, or 2 years or a month. It depends on the life cycle of your business. Okay, so the insurance is 1 year by definition. Okay. So in that case, I want to sum all those information. If I have many people changing city or changing marriage status, I will count this as a sum. Let's imagine here I have another number. Okay, we don't care, but we don't care about the numbers. But this is my value of one customer. This is the value of another customer. Sorry, these two here. Okay, then C2 is another customer, and C2 is another customer. Okay, so here the average value will be 300 average with 250. Okay, so on average is 200, right? That's the average value. But that's wrong, because when I got Mario Rossi, it spent with my company all the amounts. So the average value is the double than that. And so if the impact of this changing is non residual, so if it affects only 1%, a very small amount of data, you don't care basically. When this affects an important percentage of your kind of high spending customers, then it affects your statistics. Okay, not all of them, but in this specific case I gave you. Okay, which is of interest for the company. Please. Yeah. So the example is your colleague is suggesting we skip the customer DC1 and we use Mario Rossi as an ID. Okay. What's the problem here? The problem is the following. Let's get back to our data warehouse. Let's use this one. A nice blank slide. Okay. When I write something like this, customer, is it working? Yeah, customer. Well, it's badly written. That's customer. Okay. Then I have CD, and then I have married. Okay. Okay, so CD and married. Sorry, I'm writing too fast. I need to slow down and write better. Customer, CD, and married. Okay. It might happen the following. I want to analyze the data for each specific customer. So I might want to use, the fiscal code, social security number, an ID of my loyalty card. Okay, that is one case. In that case, Mario Rossi stays the same. It can stay the same, basically. I need to actually change a kind of ID to maintain the functional dependency, but again, use this third solution to keep track of it, okay? Another case is the customer is identified by its CD and its status. So I have one ID, one customer ID, which is actually not the specific customer. It's the customer group. So I would probably write here customer group or customer type, which is the customer type 1 are customers of Turing married. The customers of type 2 are customers of Turing non-married. The customers of type 3 are customers of Milan married, and so on. In that case, I must change the ID because the ID tells me that that customer is from Turin married or from Milan married. Okay, so in that case, I cannot recycle the ID because it's not ID of the specific customer. It's the ID of the customer group. Okay. In the end, even if you use the customer as Mario Rossi, in the end, you will need to append an _1, _2 or something because you need to maintain the functional dependency. Okay. And so you need, for the type 3 solution, to have a supporting table where you link the two, because Mario Rossi _1 and Mario Rossi _2 are probably very similar for human, but for the data warehouse, they are totally different IDs. That's an opaque check. Okay. If the string match is not the same, they are two different IDs. Okay. Fine. Thank you for the questions. Other questions? Okay. Yeah, please.
The same table, two different IDs, one that references the person so does never change over time, and one that changes.
Yeah, thank you for the question. The question is, can I have in the same table, so let's get back to the Excel sample here. Can I have in the same table, actually, you are meaning the following. I just add here fixed ID, Mario Rossi, for instance, okay? So in the same table, I have an ID which doesn't change. For instance, Mario Rossi, or you can choose any ID you like. And then we use the customer ID, the married status, or the customer ID and the CD. Actually, I'm just moving the problem to the Mario Rossi problem, because if you design the data warehouse of this solution here, okay, so fixed ID, customer ID, and married, or fixed ID, customer ID, and CD. Let's do it here. Okay. Basically, here you are doing the following. Let's see if I can, yeah, more or less. Let's do it here. You have actually not the customer, it's called fixed ID. Fixed ID. So you have the fixed ID here. Okay, it's lagging and just waiting. Okay, the fixed ID here. Then you have kind of customer ID in some ways, because given a fixed ID, you link it to some customer ID, and then you have some kind of CD. Well, you would link this to the fixed ID probably, something like this. But you don't actually fix the problem, because in the end, to maintain the functional dependency between the new fixed ID and the CD, or the married status, you kind of need to change also the fixed ID. So what we did with the customer ID and married, customer ID and CD, is what will happen with the fixed ID, because the fixed ID, to be able to not change, must be outside of dimensions. If you are in the dimensions with a hierarchy, they require the attributes of the hierarchy to be linked by functional dependencies. So in the end, what you end up having here, so this is not working, okay, this is not working. you need to have something like the following. In that case, the fixed ID is outside of the hierarchy. I can have it without any functional dependency. I can keep it as it is. But I'm losing the fact that indeed that ID is talking about the customer. So if you apply this process in an extreme way, you will have something like date, month, year. Okay, date, month, year. So you split all the hierarchies into single elements, which allows you in getting rid of the functional dependency. So in this process, there is no functional dependency between fixed ID, customer ID, date, month, year. But that is wrong because indeed in real life, you have dependency because you are not free to choose any date you want if you fix the month. You are not free to choose any fixed ID if you fix the customer ID. And so again, this contradicts the idea of conceptual design, which captures the dependencies among the data. Okay, so why this is wrong? Because this doesn't capture dependency among the attributes. Okay, so if I fix a customer ID, I'm not free to choose any fixed ID I want because they are linked. That's the reason why instead you have dimensions like this. Okay, here, why you have two different dimensions here, or three better, the store, the date, and the video game. Because given a store, you can choose any video game and any date. Given a date, you can choose any video game and any store. Given a video game, you can choose any date and any store. They are independent. And why instead, given a company, it's linked to the video game? Okay, I'm talking about this aspect here. Because given the company generates 10 video games. So I must choose one of them. And there is a dependency. Okay. Otherwise, all these bullets could have been linked directly to the fact table. No functional dependency. We can do whatever we want, but that's false. It's not working because we cannot do whatever we want because I'm not free to choose any company I want if I've decided this is the video game of interest. Okay, that's the point. Okay, thank you for the question. Yeah, so we have seen the three types of representing time. Okay, representing time and the slowly changing dimension problem. Okay, so these are the examples. This is they'll take a picture, but it's recorded anyway. So Zoom is working today, so we are nice. Okay. Now, what else? A few considerations on the workload, and then we go into the logical design, I guess. Yeah, it's there. Okay. So, oh, it's really time for the break. Yeah, it is. Okay, so I think it's right time to have a break. Okay, so see you in 10 minutes or something like this. Okay, if you can take a seat, please. We can start again the lecture. So one one key point of the data warehouse is its performance. Okay, so when you need to evaluate your data warehouse, first you need to get it right. So you need to have a good design of the conceptual part. Then we'll see later the logical design. Okay, so you need to do things correctly. But that's not enough. You might have a good design and then it's still slow. And so again, that's not an optimal solution. Okay, so how can you estimate the behavior of your data warehouse? And that's called to workload estimation. So workload estimation is how does the work that my data warehouse has to do is characterized by, is featured, is yeah, what are the main types of queries I need to address? Okay, so first, a data warehouse tend to be used for known queries. Okay, while on a database you might ask queries of any type, a data warehouse is meant to answer strategic queries or fill in dashboards, okay, fill in reports. Okay, so you know in advance which are the queries that are filling these reports, these dashboards. Okay, and so these are the standard reports or the typical queries that are run. However, depending on the results you see, you might want to do additional analysis, like data exploration or drilling down into specific trends or behaviors that are strange or unusual. Okay, and these are typical unforeseen queries. Okay, so the idea behind this reasoning is the following: if you know in advance which are the frequent queries, you can optimize those queries. Okay, that's a typical pattern. Okay, if I know that you will ask the average grade per student, I can optimize with proper structures called indexes, okay, and also with physical design, but with some strategies. I can optimize my data warehouse so that I can answer those queries. Okay, so it's like if you know in advance which is the exercise of the exam, you practice a lot solving that perfectly, and then you come to the exam and you do it perfectly. Okay, so if you know in advance something, you can prepare better. Okay, you are probably more focused on that. You don't know anything else, but you can do better that task. So that's one side of the story. The other side of the story is when instead new exercises are provided, are you able to do them? So when new queries, which are not evaluated at design time, arrive, are you able to address them, to answer those queries quickly? Okay, and that's a challenge because optimizing data warehouse means building data structures like indexes on some type of attributes. The queries might change for many reasons. You change your format of the report, you change the dashboard, your boss has new questions, the market is changing, okay, the policy is changing, the strategy of the company is changing. And so these will change over time. So in the end, you do some pre-design, or I would say during design, so at design time optimization, based on what you know. Okay, so you ask your customer, your boss, your colleague, which are the frequent queries, okay, which are the most common queries that my data warehouse must answer, and you start by optimizing those, of course. Then you do tuning after deployment, okay? So you analyze the workload by classical profiling tools, okay, which means how much resources is using, which is the average time required for it for giving a response. Okay, so on average, my users issue a query and they answer in 1 second, 10 seconds, 2 hours. Okay, and you know if that is acceptable or not. Okay. So basically the main measure of your data warehouse is the size. Okay, the larger the size, the larger data on average you need to read from disk to answer a query. Okay, to break these, you introduce indices and materialized views. Okay, materialized views are simply when you write a query, you can save the result of that query. Okay, so you write a query, which is what's the average grade for each student divided by academic year. Okay, that reads billions of rows. The result is only a few thousands of rows. You save that. Okay, and every time the original data changes, you update also the view. Otherwise, that's useless. Then you have different options. You can update it only when requested. You can update it every time data changes. That's some policies we will see later. Okay, but the idea is I use supporting structures, materialized views, and indices to be able to break the problem of the data space. Okay, so I can keep growing, but I save these structures, which are much smaller than the original database. Okay, so an index can be very small because the index basically is like the search on the surname in your phone book or the search on the phone number in your phone book. Okay, so it contains only the phone number and the name. So every time I receive a phone call given a phone number, I can look up the name immediately and show it here without reading the whole phone book altogether. And the phone numbers are ordered in the index. Okay, so that's a trick. It's like in the past when there were the libraries and you went to libraries to get physical book out of the shelf, you had a list, a printed list of authors sorted by alphabetical order, okay, of the surname of the author. And then for each author, you had the list of the books. And for each book, you had the shelf, the room and the shelf and the position on the shelf, the book, okay? That's an index. Okay, in computer science, it's like different. You have pointers to the position in your hard disk. Okay, so the page, the sector, the block, and all the stuff. But in the end, it's conceptually the same. Okay, the index of a library is a few sheets of paper, depending on how large the library is, but can be like one book is the index of thousands of books. Okay, and that's the same for computer science equivalent. Okay. Whereas the materialized view is like saving the result of a query, which is much smaller than the original data, okay? And I have it ready. So instead of reading the original data, I read the short version. In Italy, we have the Bignami version. Bignami is a famous short version of books, okay? So instead of reading the whole Divina Commedia or the whole Promessi Sposi or any other famous book in Italy, some students use the Bignami version, which is an abridged version. Okay, so you read that few pages and you get the meaning, of course, with some loss of information of the whole opera, the original book. Okay, instead of reading hundreds of pages. Okay, that's the materialized view. So I know that I need the average grade of students for academic year, for each academic year, which is 1,000 rows as a result. Instead of recomputing it every time from the billions rows which are in data warehouse, I store that result and I read from the result immediately, which is something I can keep in memory. Okay, that's the idea. How can I estimate the data volume? in the end, you estimate the cardinality of the dimensions. So how many distinct values I have for each dimension. Okay, so let's take an example here. Okay, if I have a given number of students, okay, a given number of semesters. If I 10 years, that's 20 semesters. I have, oh, sorry, I have not working, or is it? Okay, frozen. PowerPoint is just frozen. Let's wait a minute. But anyway, you have the dimensions, number of students, number of courses, number of semesters, okay? And so you tend to, killed. Okay, it has been killed, PowerPoint. It's opening again. Let's see if this works. Okay. Where is my PowerPoint here? Okay. We were at, well, I don't care about any example is fine. We can take one of the first example. Let's take this example here. That's fine. Okay. This example here. Is Zoom working? Yeah. Okay. So if I take this example here, okay, then don't focus on the others. I have the product, the date, and the shop. Okay. So what's the data volume? How many data do I have in my data house? It's a combination of the three, because in the same date, I can sell many products in many shops. In the same shop, I can sell many products in many dates. Given a what's missing, given a shop, I can sell many products in many days. But anyway, all the three. Okay. So if I have 10,000 products, I have 100 shops, I have, I don't know, 10 years. Okay, 10 years means this number of days. Okay, I basically multiply all of them, knowing that it is a superset. Okay, because in general, not all the combinations will actually exist in the data warehouse, because I tend, that's of course an assumption, I don't sell all the products all the days in all the shops. For instance, for some days the shops are closed. Some products are not sold in some days in some shops. Okay, and so in general, this is, so if you multiply 10K, multiply, so this is 10 to the power of 3. This is 10 to the power of 3 or 2. This is 3 multiplied by 10 to the power of 3, 3.6, we don't care. We have 10 to the power of 3 plus 3 plus 2. This is 10 to the power of 8. Okay, of 8. And it's 3.6 multiplied by 10 to the power of 8. So the order of magnitude is 10 to the power of 8. Okay, so it's almost in the orders of the billions, more or less. Okay, almost. That's my order of magnitude. Okay, so how many events, how many rows I expect my data warehouse to have? That's how you estimate that. Okay, and you don't care about the hierarchies, because hierarchies are just a consequence. So given any shop, I know for the shop, the city, the region, and the country, but they do not add combinations. They are a consequence. So given a shop, the consequence is it has a city, a region, and everything. Okay. So that's the idea. Okay. Where were we? Let's jump more easily with this view. Okay. So this brings us to the sparsity, which is next slide. Just let me see if I forgot something here. Yeah, the other thing you need to have a look at is the attribute length. So in each fact table, you have measures, and while the fact has billions of rows as an example, the dimensions instead only has typically thousands of rows. So let's get back here to discuss this. If you are here, okay. If I need to add an attribute to the shop. Okay, so in the shop, I have this hierarchy. I want to add a new one. Okay, I want to add, no, like this, new administrative area or province. For instance, here we're missing the province. Okay, which in Italy we have the provinces as well in between the regions and the country. So the province is actually something which can be in the middle between the city and the region. Okay, but anyway, we add a new attribute. We don't care about which. Okay, we add a new attribute, and the cost in size, in data volume of this attribute is replicated 10 to the power of 3. Okay, so this is 1,000 shops. So if I add the province, I have 1,000 times the province. Okay, if the province occupies 4 bytes, is 1,000 times 4 bytes. Okay, so it's 4 kilobytes, very, very tiny. Okay, so adding complexity in the dimensions is not typically a problem. Okay, you add them easily. Okay, because dimensions generally have a lower cardinality. They only see a portion of the problem. They only see the number of shops. They only see the dates. Okay, they only see the products. Okay. Instead, if you add measures here, or as we will see, we can do the push down, other features which brings down into the fact table something, okay, being a measure or anything we will look at later. Those values here inside the fact table are repeated billions of times. So we must be aware that everything that goes down in the fact table is amplified as storage space by the cardinality of the fact table, which typically is large, because data warehouse is generally a big data solution. Okay. Otherwise, you can just query any database easily. Okay. If it fits in memory, you don't need the data warehouse. You just query the original data. You do the join, and you live happily. Okay. Fine. Okay. So that's the point. If you add something in the dimension, small penalty. Typically, you need it. Well, if it is useless, it's always a penalty. Useless stuff, no way. Okay, but if it is something useful, it's not something you need to think about too much because it's low penalty. Instead, if you need to add something in the fact table, think a little. Do I really need it? Can I do something better? And we will see solutions to limit, to mitigate this issue in the following. Okay. So let's jump back to our, yeah. So that's it. Yeah, not all the combinations, we said it. Yeah, and that's it. So sparsity, that's the idea of sparsity. What's the point in sparsity is the following. If I count all the combinations, okay, let's get back here to understand this better. If we count all the combinations here of of the fact table is 10 to the power of 8. Okay, so it's in the billions order. Okay, in the billions order. If I introduce sparsity, so if I say not all the products are sold in all the shops in all the dates, but as in the slides here, we decided it's 10% or something like this. Or is it? Yeah, 10% of all the combinations. Okay, this affects our computation because if it is 10% only, okay, here this becomes 10 to the power of 7. Okay, only 10% of the combinations are actually present. Okay, this is true if you stay at the lowest level of granularity, which is shop, date, and product. But if I start growing in cardinality, in granularity, so instead of having date, product, and shop, I group by, for instance, let's add some attributes here. So we have them, oops, sorry, here. We grow to the type of product, okay? We grow to the city of the shop. We grow to the month, okay? So if you focus on these, so we have type of product, month, and city. Okay. These are, of course, less in cardinality because I only have, I don't know, instead of 10,000 products, I only have 1,000 types. Instead of 1,000 shops, I only have 100 cities, and so on. So I have smaller numbers. But what about the combinations? Okay, let's write numbers. Here I have 1,000 types, 100 cities, and how many months? It's 12 by 120. Okay, because it's 10 years for 12 months. Okay. So if before I had 10 to the power of 8, but only 10% of the combinations actually were present, so I deducted to 10 to the power of 7. Now, with 1,000 types, 120 months, and 100 cities, the probability that some of these combinations do not exist in Dedham House is very low. So probably all of them are there. Because the probability that I didn't sell in any shop of the city, in any day of the month, none of the products of that type is very low. Okay. And so here in this case, I have all the combinations in place, even if the original data was kind of sparse because it was only 10% of the original data. Okay. That's the idea. So that's what this slide is depicting here. Okay. So you have many missing values here. Okay, you have many missing values here. But when you group them in the whole block, if at least one is present, you can compute the aggregate. And so the aggregate data is much less sparse than the original one. Okay. Fine. So as it is, we finished with the conceptual design. We will get back to understand better some patterns which rely on the logical design as choices. Okay. So now instead we move to the logical design. What's logical design? Logical design means designing the tables. So which are the actual relational tables where I store the data. Okay. Luckily enough, the translation from the conceptual design to the logical design is quite straightforward. You will have an exercise in the exam, but it's only 1 point, I guess, or 2 points, because typically it's kind of easy. Okay, if you learn the patterns, it's sort of mechanic translation. Okay. However, it's interesting to understand why it's done like that and which are the pros and cons. Okay. So here, the cornerstone of the data warehouse is that differently from databases where you have normalized data, for those of you who doesn't know, means that if I have a relationship between a city and the province, so a city belongs only to one province, I have the student linked to the city. Then I have another table linking the city to the province. I do not duplicate the province. Okay, that's an example. Or if I have this temperature sensor in rooms, and the rooms belong to a university, and I'm monitoring the temperature of all the universities in Italy, I have the room 1P, which belongs to Politecnico, and I write room 1P belongs to Politecnico. So I have a table with all the rooms and belonging to Politecnico, and then I link the sensor to the room. So I don't write this sensor is room 1P and is Politecnico, because otherwise for all the sensors in Politecnico, I would duplicate the presence of the Politecnico information. Okay, so the idea of normalization is you write things only once in one place. Okay, just let's use Excel because this works better if you use an example. Here, let's use the example of the sensor. Okay, so sensor ID. That's sensor 1, room 1P. Okay. Then I have another table which says room, university. Okay. So 1P. Of course, there is a problem because the room 1P can be present also in other universities. So we need to have another ID. So we can use, I think the rooms actually have a kind of code which is unique. So can be something like 1P X epsilon Y. Okay, we don't care about this. Just to give you the example of normalization. Okay, this way, and that's the university. Okay, so here, given these two tables, if I join them, I can answer the queries: where is this sensor? Which university is this sensor belonging to? Okay, and of course, if I have other sensors, let's try this. Okay, yeah, seems working. That's nice. And I can have the same here. No, sorry, that's not the right. Okay, okay. All these sensors are in the same room. The room is in Polytechnico. Okay, so you see the relationship between the room and the Polytechnico and the university is stored only once in a separate table. Okay. The same for a student. So if I have a student here, well, I can actually write student here and city. And here I can write like Turin. Okay. And here I have Turin is in, let's say, Italy. Okay. So that's city and that's state. Okay. So that's the case. Turin is in Italy. That's it. And I write it only once. That's not what happens in data warehousing. This happens in databases. That's normalized because I do not repeat this relationship more than once. Why? Normalization is good, even if in data warehouses we will not use it. Is good because normalizing data allows you to avoid duplication and to easily fix problems. So if you have an issue here with Turin and Italy, and you write wrongly, I don't know, France, for instance, or well, you can also have a misspell, okay? Something like this, okay? You fix these and automatically all the queries using Turin will be fixed, okay? That's the advantage of normalizing data, besides the storage and the tidiness of the solution. What's the problem here? The problem here is that every time I want to collect all the students from Italy, I need to do a join. Okay. If I don't join the table on the left with the table on the right, I don't know which students are from Italy. Okay. And the join is a heavily computationally intensive job. Okay. So it takes time. If you have an operational database, which is typical database for orders and everyday business, the database tend to already be partially in memory, tend to be small because it contains only the working set of information you're working on, the recent data, okay, the open orders, okay? And so you tend to afford doing the joins in exchange for the tidiness and the advantages of being normalized. In data warehousing, instead, you have billions of data. You have the whole historical memory of your company, okay, and possibly all the sources, different sources of data. So it's huge. And doing a join, since it's heavily computationally intensive, if you do something which is heavy on a small amount of something, it's affordable. If you do something which is heavy on a large amount, that's unfeasible. Okay, so running at your maximum speed, you can sustain that for I don't know, a few minutes, a few seconds, depends on how trained you are. But you cannot keep the highest speed you can reach, like in a 100 meters run, for kilometers. Okay. And you know the average speed of marathon athlete is lower than the 100 meters runners. Okay. Okay. So that's the same here. If you have the operational database, it's like doing the 100 meters. You can do high speed. So even if it takes a lot of energy to run fast, you can sustain that. Instead, data warehouse is the marathon. Okay, so you cannot go at that speed. So you need to change your strategy, and you need to have the joins avoided at most. You cannot avoid them all, but at least when you can, you try to avoid the join. To avoid the join, you pre-compute the join, and you put the data already joined inside the data warehouse. Okay, and in our case, what happens is the following: that here, instead of having a separate table to join with, I add the, what's wrong here? You add, okay, it's not working. Okay, that's incredible. Where are we? Okay, let's try to move the window. Typically, refreshing the window helps a little. Not in this case. Oh yeah, it's working. It's really refreshed badly. Okay, let's try if this works. Yeah, it's working here. Not really. No, not really. Like if doesn't follow the window. Sorry about this. Well, I can open a new sheet of Excel, no problem. Okay, new sheet of Excel. Excel. Where is it? Okay. Okay. So here we have the student ID. We have the city. We have the state. Okay. And so S1, S2, and so on, Turin and Italy, they're all in the same page, the same table. What's the problem here is that you might have here something like France or errors like this. Okay. This might happen in a database, in operational database, because typically in operational database, data is collected by external sources like a form on a website or a person inserting data. Okay. So that might break things. In a data warehouse, instead, this should not happen. Okay, it typically doesn't happen. Why? Because the data ingestion is done by the ETL process, the extract, transform, and loading. So it's automatic. It's not a human inserting data in data warehouse. Okay, and so this doesn't happen because during the ETL process of the data ingestion in data warehouse, you do the join, and so you generate the result of a join here, which is this one. Okay, so the join is done during the ETL, and then we store the result of the join in the data warehouse with all the columns we need. So if we need also the region, we insert also the region here, which is totally redundant information. Okay, that's totally redundant because you copy this information all these times uselessly. Not uselessly in reality, because it would have been useless if we had another way to get that data quickly. But since getting this data would require a join on a billion rows fact table, which is unfeasible, kind of unfeasible, or at least inefficient, by storing this data, I'm trading space and time. So I use more space, but here I'm in a dimension because the city, region, and state are on the geographical dimension. So I have 100 cities, I'm wasting 100 rows. I have 1,000 cities, I'm wasting 1,000 rows. So small amount of data. However, I save a join with the fact table, okay, which is very large. So I'm trading off space and time. In this case, I waste the space, I invest, not waste. I invest the space to get faster times, okay, to save the time of join. Okay, so that's the idea. So that's denormalization. Okay, let's see, I have the pen. Yes, that's denormalization. Okay, so basically it's pre-computed some joins. Okay, and data redundancy, it's exactly what I said. So you repeat many times the same values. Okay. So how do we build the logical schema? Okay, let's see the example, then I get back to the slide to check. This is my data warehouse. Okay, I finished my conceptual design. I have my sales with the quantity and the amount. So quantity is number of items. Amount is the income in euros. Okay, they are the totals. Okay, so this data warehouse tells me, given a product, so for each product, for each shop, and for each week, how much items, how many items I got sold, and what's the amount of income I got in that week for that product, for that shop. Okay. So to create a solution for these, I need here to have at least the week ID, okay, or a kind of time ID. Let's see what happens. A product ID, and a shop ID. If I have these, a shop ID. If I have these values, okay, then we can remove the state. Okay. If I have these values and these are my primary keys, okay, so I underline the primary keys. I can also use the bold. Okay. A table like this, where I add the quantity and the amount. I didn't want this. This is a wrong assumption of Excel. Okay, like this. Okay. Yeah, I want them this. Okay. A table like this is able to provide me with what I need. Okay, let's also use the borders. Okay, because I can change the week or the product or the shop and insert the amounts. Okay, so given a specific week, a specific product, a specific shop, I only have one line. Every time I change any of the week, the product in the shop, I generate a new line. Okay, this is the property of the primary key. So primary key with 3 attributes generate unique, not couples, but tuples of the 3 attributes. Okay, so I cannot have here another row having the same values. So W1, P1, and S1. That's not acceptable. Okay, because that's the primary key. So I don't know if I can. No, I wanted to cancel these. Let's see if there is. Yeah, that one. Okay, I cannot have that because it would break the primary key constraint. Okay, the primary key must be unique, please. So, yeah, yes. The question is, do we have a redundancy here or not? That's interesting. The answer is not, but let's see why. If I introduce redundancy here, so I start introducing the month. No, I don't want that. Okay, let's copy this behavior like this. Okay, the month. I don't know the city of the shop. We can add the category of the product and all the stuff here, something like this. Okay, if I add this, Let's color them differently. Okay. I would add redundancy, but I would add redundancy to the fact table, which is billions of rows. So these cost a lot. I must be absolutely sure that it is required with no other options. So is there any better option instead of adding those rows? Yes, there is. Okay, so in the fact table, we do not add redundancy because the fact table, as an hypothesis, is of high cardinality. Okay, because it is low cardinality, it's a fake data house. It's trivial information. So you do whatever you want. When you have no constraints in terms of resources, it's not an engineering problem. You do whatever you want, it works. Okay, it must be only correct, not also efficient. Okay, so that is why this is wrong. Okay, so this is wrong because introducing these into the fact table would introduce an inefficient redundancy. Okay, due to the high cardinality of the fact table. So in the fact table, we insert only the ID of the dimensions and the measures. Okay, that's it. Instead, we introduce redundancy in the dimension tables. So this is the fact table. Let's write here fact table, which has measures plus one ID for each dimension. The ID for dimension, again, for the purpose of efficiency, cannot be any ID you want. Okay, imagine that the shop ID or the product, let's call the product ID. Product ID is, I'm sorry about the advertising. I just choose a name. You can choose any name you want. Samsung Galaxy S Ultra Plus, whatever. Okay. So imagine you have this ID. Okay. It's also misspelled. And all of them are like this. Okay. The full product name, which contains Ultra Pro Plus, whatever. Okay. This is for billions of rows. And for billions of rows, you are storing such a large string of data. Inefficient. It's a waste of space. Okay. And also searching there, it's inconvenient. Okay. So instead of using the real ID of the product, of the shop, of the week, of anything, we use the so-called surrogate keys. Okay, surrogate keys, then in the slide there is name, okay? Keys, IDs, primary keys, generated on purpose, okay? And they are generated to be short and compact. So you typically use numbers, okay? So here I will have week number 1 can be even only 1 because I know it's week. Product, it will be product number 1. Shop will be shop number 1. So the shorter it is, the better. Because if I have an integer, okay, I can use a long, which is a few bytes, 4 bytes, let's say, okay? And I have billions of combinations with 4 bytes, 2 to the power of 16, whatever it is. 4 bytes is something more. But anyway, you have a very large number of combinations with a small number of bytes. Instead, if you use the strings is much larger. But much larger means 40 bytes, 10 times. But 10 times for billions of rows means that instead of having 1 terabyte of database, of data house, you have 10 terabytes only for the product. Then you have, again, 10 times for the shop. And so you have terabytes and terabytes of data useless because every terabyte counts when you need to read it. The disk I/O is expensive, is the bottleneck. Okay? So space is cheaper than time, but if you waste it, it's inefficient, no engineering solution. Okay? It's a wrong solution for an engineer. Okay, so here we use instead surrogate keys, which are short keys, in the end integers, okay, which we use and generate for the purpose of matching the data in the data house. During the ETL, extract, transform, and loading, so the ingestion of data, I have Samsung Galaxy, everything plus whatever, and a long string. I match it to ID number 1. So in the data warehouse, here I write 1. Then in the dimension table, which is smaller, much, much smaller, okay, I can write the full name, because then my boss in the report wants the full name, okay? So I keep the original data, but not in the fact table with billions of records. I use it in the dimension table, which is smaller. So I pay less cost in terms of space, okay? So that's the idea, okay? That's the idea. So the fact table is translated into a table containing 1 column for each measure. That's easy. I want to measure those information. I write the measure. And 1 column for each dimension. That column contains the surrogate key. The surrogate key being typically an integer, but anyway, an auto-generated number or short ID by the data warehouse, which has basically nothing to do with the original value. Okay, just happen if it is an auto increment, just happens that with the first time I see a new model of product, I assign a new free ID, and that will be the ID forever. Okay, that's it. Because actually, this is just used for optimizing disk space there. Okay, now how do I build the dimensions there? Then, dimensions build the primary key of the fact table. Okay, so if I have week, product, and shop, I cannot answer which is the daily sales. I cannot, because the smallest row is the weekly sales of a product in a shop. Okay. Then how do I build the dimensions? The dimensions will be, I can write one here, for instance. Okay. It's keeping the formatting. Okay, so let's delete everything here and I do a new one. Okay. So dimensions. For each dimension, I have a table. In general, 1 table is enough. In some special cases, I need more than 1 table. But in general, most of the times, 1 table is enough. So let's say the week, okay, let's say time dimension, okay. So let's call these dimensions as a title. Time dimensions has, of course, the week ID, because I need to join my time dimension with the fact table. When they ask me, select the data for this month, there is no month in the fact table. How can I know which month, which rows should I take? I need to join the month, which is in the time dimension, with the fact table. Okay. And how do I join it? By means of the surrogate key related to the time dimension, which is week ID, because the smallest time is the week, but I can call it time ID, no problem. Okay. It's an ID. The purpose of connecting the two. Okay, so the week ID. Then I look at my design. I have week and month. So in that table, I put the week and the month. Okay, so I get back here and I put the week and the month. So these can be 1. A week can be, I don't know, week 1 of year 2024, for instance, and the month can be January 2024. Okay, that's an example. If you had the year, you can also add the year 2024. If you add something like, no, the semester, you can also write semester 1, 2024, and so on. Okay, if you had the month of the year, you would have, let's add it anyway, even if it's on the gray side, month of the year. you would have January. That's month of the year. Okay, so I would better do the following. Let's put it like this, and let's put it like this. And like this. So these are the wrong stuff. Okay. Okay, that's it. Okay, and you copy. Of course, in this case, you only have week and month. Okay, I have added the others to show you how you do that. Okay. Then I have a week two. Week two will be something probably week 2, 2024. I don't know. But the week ID, which is surrogate, and the corresponding week can be totally unrelated as long as they match one-to-one. So just to give you a general example, week 2, so here I can have the number 72 for week 2. Then I have number 64 for week 3. Okay, we don't care about it. Okay, it's transparent. We don't even see that in our reports. Okay, and then all the rest. Okay, all that information is duplicated here. So let's see if I can do this, but I think it's, yeah, no, 2024. 2024. Yeah, and that's the same here. So let's do like this. And the same. Okay. Like this. Okay. That's the case. So you see a lot of redundancy, but the redundancy is in the dimension table. How large is this? The number of weeks. You know, for 10 years, it's 500 weeks. Tiny numbers. Tiny numbers. Okay. So I don't care about this redundancy. It's not wasting space, but it's saving in joins. Okay. Time dimension, then we have the product dimension here. So here we have the product dimension. Okay. Which has, of course, the product ID. Okay. Because that's the join key, my surrogate key for the join. And then I go and look for the other attributes in my table: product, supplier, type, and category. Okay, product, supplier, type, and category. So here I have the product, and this is the full name, or the ID used, the barcode can be, or any other. It's also called SKU sometimes in product management. Okay, SKU, it's, no, it has an acronym, but it's also called that. But that is the original data. Okay, so the product ID is generated by the data warehouse. It didn't exist before. The product instead is the value of interest by your boss, by your marketing team, by your customer. It's something you take from there. It's a string, it's an ID, it's a name, it's a barcode. We actually don't care. Okay, that's the product. And then we have the rest. So we have a supplier, we have the type, and we have the category. Okay, sorry for the typo. Type. Okay, that's it. And again, here we have number 1, the product. You choose the name. Okay, anything you had in the original database. Okay, and then you have the supplier. Okay, I don't know, you choose a supplier, you choose a type, and so on. Smartphone, and you choose the category, electronic devices. Okay, something like this. Okay, that's it. So you see what happens here. You are losing the functional dependency. You can still understand the functional dependency by looking at the values. So you see that here, the year is collecting all the January's 2024. So the year is collecting the month. You see it from the value, but you don't have any conceptual indication of it. Okay. So it's not the order of the columns which goes higher in the hierarchy, because otherwise, when you have this with product, supplier, type, which one you choose? Okay. So as it is in relational databases, the order of the columns is meaningless. Okay, there is no meaning in the ordering of the columns. Then my suggestion when you design tables is to put first the primary key and then the rest, because it's much easier. But that's a conventional behavior, okay, for your reference, because it's easier to read, it's easier to correct your exam, it's easier for your boss if you prepare documentation like this, okay? So that's kind of convention. First the primary key and then all the rest, okay? Here, the primary key in our course is either in bold or underlined, like, sorry, like these. I use both because I have time to click both, but otherwise you choose either bold or underline, okay? When we wrote on paper before the COVID, we use underline, it's easier because doing the bold on paper with your pen is more difficult, you know. So we use underline. Nowadays, we click on bold, it's easier because in the exam solution, the bold is easy to do. It's one click away, whereas the underline is probably 2 clicks away, so it's just less efficient, okay? That's it. And then we have the third. So we have the week ID, the product ID, and the shop ID, okay? And the shop ID, so here we have the shop dimension. We have the shop ID, and then let's see, we have the shop, the salesman, the city, and the country, okay? And so we have the shop, salesman, the city, and the country. So shop ID is 1, the shop is any name you want to identify the shop. So that comes from the original database, okay? And then here you have everything else, okay? So you have these, and you have these, and you have these, okay? So you see Turin and Italy are the same. So if I duplicate these, I insert new data, I still have Turin, Italy many times, okay? Anything else? Third product, and so on, okay? That's duplicated, okay? And again, I need to identify the primary key. Let's use the bold and underline, and that's it. So this is the shop table. This is the product table. And this is the time dimension, like this. And that's the fact table. Okay, that's how you build that. Then we need to see special cases, but that's the default. So you see, I think it's quite simple. I mean, at least in the normal case, it's kind of mechanic. Okay, you copy the surrogate key, you add attributes. That's it. Okay, so let's check everything here. Yeah, please. Oh, yes, sorry. Yeah, thank you. Yeah. Thank you. Yeah, that's it. Great. Okay, you can take a picture like this. Probably you can see almost everything there. Okay. Now let's see special cases, because I can do different stuff. Okay. For instance, if I challenge my assumption of denormalization, okay, I can say I have tens of thousands of products. Should I repeat for all of them? Turin, Italy, Turin, Italy, Turin, Italy. Wouldn't it be better to say Turin, then country ID, which is a small value, not like a string in a country. And then I have another table with the country ID and the country. And only when I need to check for the country, I do that join. Okay. We will see this is an optional solution, which doesn't go as the best one at the moment. Why? Because nowadays disk space is cheap, and so you prefer to store it redundant but be faster in answering than having to look up. Okay, but that's a possible solution. Please. Yeah. definitely. So the question is this different implementing this into SQL or NoSQL? Yeah, it is different. We'll see in the second part, NoSQL, yeah. Okay, so I've just explained all these slides. Let's see them together. You see here, you have the fact table with the measures. Okay, so these are the measures. These are the measures, okay? Then you have one ID for each dimension. Okay, so you have the dimensions here, like this. And then you just copy the attributes of the hierarchy. That's it. Okay, as easy as that. Okay. This is what happens as a schema. Okay, it's called star schema. Why? Because you have in the middle, and then you have all these dimensions going as if it were a star. Okay, that's called star schema. Okay. And in the end, what you need to do is a join with the fact table and the required dimensions table. But the join happens to be on a very tiny ID, which is called the surrogate key. Okay? And so it becomes efficient. And this is the only join you need. Okay, so you need to optimize a specific operation, the join between the fact table and any of the dimensions table. That's it. After that, no additional join operations are required. So at most, you do a number of joins which is equal to the number of dimensions. That's bounded. Okay, and you know in advance, those are the joins you need to optimize. So you will go and index definitely these columns. Okay, you probably also store the data in such a way that it is convenient to get it, and that's it. Okay, that's the star schema. Yeah. Pardon? So in which case I use the denormalized version. Yeah, that's the snowflake. It's coming in the slides. It's coming in the slides. So in the snowflake, so that's the star schema. What is the other option? The other option is I have a less redundant solution, so more normalized, like in databases, but at the cost of an additional join. That's called snowflake schema. Okay, let's see then we get back to the slides. Let's see if I told you everything about these. Yeah, surrogate primary key, we've done it. One table for each dimension. Dimensions are, hierarchy are not explicit, I told you. Totally denormalized, yes, data redundancy. And the fact, one fact, primary, and measures. Yeah, that's it. Okay. Inside the snowflake is like this. Here, I have the same behavior until this. This is the same as before. Okay. But then, to reduce the redundancy, instead of saying always, this city is in Turin is in Italy, Turin is in Italy, Turin is in Italy, I remove this portion here, Turin, Italy, and I generate a new table, which is country ID country. Okay. Actually, it's done in the slides. It's done in the city. We can use it the city without the additional example by me. Okay. Here you split on the city. Here you see this city here goes there. Okay. So you do not repeat Italy for all the cities of Italy. Okay. But you use to look up the city ID and check the name. Okay. That is what you would do in databases normally. Okay. That's called snowflake because the star has only one level outside the fact table. Okay. Each dimension has a table modeling the whole dimension. So given the fact, you have one jump to the dimension, that's it. One join, that's it. That's a star. Snowflake because you have different jumps. So you jump from the fact table to the first level of dimension. That's the first join. Then you can do additional joins. Okay, so here, if you want to select all the sales from Italy. Italy is here. You need to check Italy, get all the cities ID of Italy, do the join with the shop, and do the join with the fact table. So you do two joins. Okay, so one join here and one join here. Two joins to answer that query. What do you, so you pay in terms of time, execution, performance, okay? What you get is less disk space because this shop is smaller and this city is smaller, okay? Because the city is only 100 cities. The shops are, I don't know, a few thousands, okay? And so I have less repetition, less redundancy of the Italy repetition, which happens to be that one, okay? And also the city would be a city ID. So instead of the string, I have only the ID, which is small, okay? So that's the advantage. However, yeah, you see, this is the example of another snowflake schema. So here they moved the city, which is here. So the shop has become two tables, but also the type of the product. Okay. So you can split it as you would do in a database. Okay. Every concept becomes a new table and you do the join. So you're paying the join cost, but you're saving on disk space. Okay, this is typically inconvenient. Yeah, okay. The question is, when do we have to do the snowflake and when do we have to do the star schema? The snowflake schema is currently taught in data warehouse courses just for historic references. But you always use the star schema nowadays. That's so easy. They have the same information, yeah. Yeah. The star consumes more disk space. You have the same information, but less repetitions. The point is here, the question is why the star schema uses less disk space. This is the star schema, okay? That's the star schema. I do for you the, oh, sorry, the snowflake, okay? Snowflake, here I have CD ID, that's 111. I have no country. I have CD. I have CD ID. One, Turin, Italy. Okay, that's it. Okay, you see, here you're wasting Turin, 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 Italy, Italy, Italy. Okay, strings, a lot of bytes. Here you have number one, small byte, 1 byte, and Turin, Italy only once. If you repeat this for a few hundreds of rows, that's it. Disk space, yeah. So the question is, when do you prefer to do a join? When do you prefer to save disk space? In general, you always try to save time. And if join means time waste, and you can pay, so you can save time paying in space, that's typically convenient. Of course, depends on how much. Because if you save, I don't know, 1 millisecond and you pay petabytes of data, yeah, but in general, I mean, we would need to be very specific on a use case. But in general, you tend to use more space if that allows you to be faster. So if you avoid a join, you can pay in disk space. And you see here, how much do I pay? Well, I have 1,000 shops, 10,000 shops. I'm paying few kilobytes or megabytes. No way, it's convenient. Okay. Fine, please. You would use what here? Yeah. So you would remove the year. Okay. The problem of removing the year. So the question is, what's the difference between that one? Well, let's use the month. Okay. What's the difference between this month and this month? Right? Yeah, the same. Well, we can write Jan, so they're exactly the same. No, it doesn't allow me to write Jan, but that's the point. One, the month with January 2024 has a functional dependency with the year. Okay, so when I group by month, January 2024 is different from January 2025. They're two different months. When I group by month of the year, I will put in the same basket Januaries of different years. Okay, so that's the point. Yes, you can get the same result by grouping by month of the year and year. Yeah, but you're grouping by two attributes, whereas you can group by one, which is faster. Again, it's efficiency. The point of efficiency, I'm kind of stressing this, it's because when you have tens of terabytes of data, you write these once overnight, and then you are faster before. It's like a race car. You waste a lot of time, you invest a lot of time in preparing the car to go faster during the race. Instead, for a normal car, you don't waste that much time. It's not working, okay? So this is, I'm wasting space, which is something I pay overnight during the ETL for the hard disk, which I can buy, for being much faster in answering the queries when I need it during the race. That's the idea, okay? Please. Yeah. So the question is, if we have data only from one city or one state in a startup, okay. In general, given the experience we have in data housing, you would go for the star schema all the time. That's it. Okay. We will see next lecture some cases when you use a kind of snowflake approach, but you're forced due to the choice. For instance, a multiple edge, the book author. You cannot manage a book author with star schema, purely star schema. You need a piece of snowflake, but that's kind of compulsory due to the technical limitations. It's not a choice. So if you have the choice, you choose the star schema. If you don't have the choice, no choice. You choose all the only thing you can do. Yeah. I would go for the same answer. Always star schema, always privileging the favoring the time and wasting a little space. For sure. Yeah. No, yeah.
So what if you have a very huge fact table?
If you have a very large fact table, what happens here? If you have a very large fact table, yeah, but the point is the join operations between the fact table and the dimensions are unavoidable. So you must have them. You cannot avoid them because otherwise you would right. You would do this. You would do this if you avoid this one. That is avoided join, but that is a killer operation because you are saturating your billions rows with a lot of data. That's paying too much space. I think this is the good example. This is the example. Yeah. Okay. Fine. So no laboratory tomorrow. I put a notice in the teaching portal. So we start laboratory next week. And so we meet on Thursday, right? Great. Okay. See you. Bye bye. Thank you. No labs tomorrow. No. What I'm talking.